So welcome everybody, and thanks for making it today. And as you know, today is about measuring reactivity of supplementary cementitious materials. And because we are a company at Calmetrix that sells Calorimeter, the Calorimeter, of course, and everything starts with setting the stage. You all work in this space, so you know all of this stuff, and you set the stage yourself for yourselves at conferences and in your daily work. But evidently today we experience that there's a need for more and new supplementary cementitious materials because of regulatory or social pressure. We have CO2 emissions reductions that we all need. We have SOx reduction that brought about a different way for coal-fired power plants to operate, where they use a different type of coal. They use more sub-bituminous coal for the lower sulfur content that shifts the class F ash to the class C ash. We have gas prices going down, and that means less coal power overall, and so on, so on, so on. And along came the construction boom for the last maybe almost decade, tougher specifications. All this makes for less supply and more demand, and especially our traditional SCMs, supplementary materials like glass F ash, granulated blast furnace slag, silica fume. There's a shortage of all that. At the same time, there's more demand. So a lot of you today that are present today, I know, work on accelerating the research to fulfill the need for new sources of SCMs. And as you accelerate this research, it's of course of interest to be able to characterize those materials and to, in one way or another, measure the reactivity, because it tells you about the efficiency of it, and it tells you of the potential that these materials have. And when we look at the SCMs that are of interest, there's a wide array of things. I've seen people look at everything in this industry, everything that they could find. I've seen literally people grinding up all sorts of weird stuff to see if the result of it can be reconverted into a supplementary material to put in cement, and for good reason, because concrete being the most widely used material in the world, it consumes a lot of matter, and so everything you could find that is somewhat abundant is a good idea to try to stick it in concrete if it works. So with that said, you can look at the phase diagram that you have on the right, divided into different corners of calcium oxides, silica oxides, and aluminum oxides, and you can look at how you classify those materials, and you can loosely see that towards the left you have hydraulic reactions. These materials fall into that category. Towards the right you would have pozzolanic reactions. When we look at reactivity, we pretty much look at everything, and for good reason. In calorimetry, you can measure any reactivity. Anything that generates heats or absorbs heats, for that matter, can be easily measured with the calorimeter. But truth be said, most of the materials that people look at these days would probably fall towards the right-hand side of the diagram. And we talk about calcined clays, class C ashes that we already knew, but where we try to find a way to use more of it, because now there's more abundance with the use of sub-bituminous coal. And recycled glass, perlite, natural pozzolans, of which there are a lot of different varieties, different styles of natural pozzolans, and so on, so on, so on. So everything that we name here and everything else could in some way, shape, or form be used to use in a calorimeter to test for the reactivity of it. And of course, I need to go a little bit quickly in how an isothermal calorimeter actually works. How is it designed? So while a lot of you already know how this works, for those who don't, I will make a quick overview. At its simplest form, it's designed as it consists of only three basic elements. You have an insulated box, and that insulated box is actually the thing that you can see here on the outside, this frame. And within that box, you maintain the temperature very constant, usually within 0.02 plus or minus degrees C. So it's very constant in there. It's maintained by an airflow, and that's all it is. So constant airflow gives you a constant temperature in there, so it makes it a very efficient, very, very precise curing chamber. And on the bottom of that, you have a heat sink. Now that heat sink is generally a big piece of metal, and the function of a heat sink is to maintain precisely the temperature very, very constant and very inert in there. And this heat sink will exchange heat with the sample. So in this case, you actually have a sample on the reference. In the sample, you have your active material, and this material is the one that reacts in some shape or form. And the reaction here is the one that generates heat, or sometimes absorbs heat, although in cement reactions that's not the case. And you have a reference with an inert material. And what you do, you compare the signal from the sample with the signal from the reference. You actually subtract the signal from the reference, and that way you get rid of noise. So that's the main purpose of that reference. In the sample itself, you could put different kinds of things. You can, of course, today is about cement, but just for general information, calorimeters are used in many other fields of application. Anything that has a reaction, whether it's biological reaction, or a chemical reaction, or a physical reaction, can easily be tested in there. For example, people use it to test bacterial growth, and you could look at food preservation studies, shelf life, and things like that. You could put insects in there and see how they respond to stress and to stimulation, see what their metabolic response is. So anything that you could think of that generates or absorbs heat can be put in a calorimeter. For our purpose, of course, cement materials, binders, supplementary materials, generally everything we use in cement have an influence on how the reaction occurs, and therefore have an influence on how the heat is generated, and we can measure that. And the way this is measured is actually also quite simple. It is you have the heat sink on the bottom, you have the sample on the top, and in between you have this little black part that is squeezed in between. That's the heat flow sensor. Heat flow sensor is a semiconductor, and when in the sample you have a reaction going on, let's say a cement hydration reaction, you would have a slight temperature gradient between the sample and the heat sink. And that temperature gradient is measured in the heat flow sensor in the semiconductor, something called the Seebeck effect, and it's converted into voltage. Now, we measure that voltage, and that voltage is the one that is linearly correlated with the thermal power or heat flow. So the heat flow flows from the sample to the heat sink in the case of a cement reaction. So the sample heats up, and that heat escapes through the heat flow sensor into the heat sink. That's how we measure it. And as we measure that, we get some nice curves. These are the typical curves that you would see for cement-type materials. On the left-hand side, you can see thermal power curves. That's heat flow. So heat flow or thermal power is measured in watts or milliwatts or microwatts per gram. And it shows you essentially the reaction kinetics. It's a very, very useful way of looking at something. So one thing you have to see and understand about calorimetry, the beauty of it is that you get a continuous curve. You get from time zero of the reaction until the time you want. You can get everything, a picture of everything that's going on in there. There's hardly anything else in your testing equipment that does that. XRD doesn't do it. Physical testing, like compressive strength testing, doesn't do it. You only have results at certain points in time with those methods. With calorimetry, you actually have a continuous curve. And that's a beautiful thing, because you can see how the reaction evolves, especially for the kinetics. The kinetics of the reaction is a little bit like the instantaneous speed of the reaction, how quickly it goes at any point in time. Whereas on the right-hand side, you have the total accumulated heat, which will be actually the integral of the curve on the left. On the right-hand side, it's the total heat since the beginning of the reaction that made it through the heat flow sensor. And that is actually like a distance traveled in the reaction. How far did it go? How much progress did it make? How much did it progress? So, and that is a little bit like measuring the total reactivity. Those who know those curves know that you would use, for example, thermal power to infer estimates of setting times, or look at maybe sulfate balance and things like that, and that you would use total heat for things like maturity, which is a proxy for compressive strength gain. In our case here, for the total reactivity, we will mostly use in today's presentation total heat as a proxy for total reactivity of the sample that we look at. So how do we actually go about measuring the reactivity of supplementary cementitious materials in a calorimeter? So the one big thing that I would consider a flaw of a calorimeter and I do love calorimeters, but I have to admit this is the one thing that makes it imperfect, is that it's a non-specific method. And what we mean by that is that a calorimeter cannot help you easily distinguish between different reactions that occur at the same time. When you look at a sample and reactions that go on in there can be multiple reactions going on at the same time, and you get one single curve. And it's sometimes very difficult to interpret that, knowing that there's several things taking place at the same time. So you have to try to isolate them. In our case, you could very well have an overlap of the normal cement hydration reaction and other reactions that come from the Portland itself, and at the same time, reactions that are due to the SCM in the mix. And to separate them out, we have to get rid of all the Portland things. So everything that's related to Portland cement hydration, we have to get out. So we will actually not use a true Portland cement when we test for reactivity of an SCM. We will use what we call the synthetic Portland cement environment. And that synthetic Portland cement environment is just an aggregate of all the elements that come from the Portland cement and that are used by the supplementary materials to create, well, typically calcium silicate hydrate compounds, so CSH compounds, or calcium aluminates, things that are inherent to the reactivity of the SCM itself, but and that they get from Portland, whatever is left over in the Portland cement, but that do not give the typical reactions, cement hydrations that we have in Portland cement. So when we create this synthetic environment, we can measure only the reaction that are due to the presence of the SCM utilizing those materials. So typically, we would want to have a solution where we have calcium hydroxide, which is what is left over from the cement that the SCMs use, and some alkali. And the alkali are there, they mostly help with the solution of glassy phases. And they're also available generally in cement. Now, thankfully, to make this a little easier on us, we can use a standard that came from RILEM. So RILEM has developed this standard a few years ago. It's quite recent actually, and ASTM is currently working on a draft method. The method is on the ballot for a standard there, but the AST method is actually largely inspired by RILEM too. So it is essentially one and the same. It's the same as the RILEM method. There's no big difference between the ASTM that is about to come out and the RILEM method. And one thing that is useful that the RILEM method gives us is it gives us a recipe for what we should put in there in our sample to get a synthetic Portland environment. So in there we have, of course, besides the SCM, we will have water, of course, we'll have calcium hydroxide, we will have potassium hydroxide that brings a little alkali, and also more hydroxide in solution that lifts the pH a little more. And in the RILEM method, they also added some other components, a little bit of calcium carbonate, and also some sulfates. Now, these are in there really for distinct reason. This RILEM method was mostly sponsored by the team of people that developed LC3, which you may be familiar with. It's the limestone calcined clay cement. And if you don't know it, it's a beautiful initiative. You can certainly look it up. You can Google it. It's an initiative that's a collaborative effort for different institutions around the world in academia, different industry partners, and they've done an immense amount of progress and really started with something that was a concept and brought it to something very tangible. So it's called the LC3. You should look it up. And because this standard was initially sponsored for the main reason to check the reactivity of calcined clays, they added also the elements that they deem necessary to make the LC3 system work, which is the calcium carbonate and the sulfate. Now, we have that recipe now, and it gives you proportions, so you have to respect certain proportions in there. You can, of course, read the standards, the STM when it comes out, or the RILEM, but it tells you things like the ratio for the SCM to the calcium hydroxide has to be 1:3, et cetera, et cetera, et cetera. So as long as you have the right ratios in there and respect that, you should be fine. Now, the RILEM method gives us some other indications. It also gives you an indication and guidelines about about different things on how to stage the experiment. First of all, it actually, in fairness, it doesn't give calorimetry as the only method. It says there's two good methods. It's you can have either calorimetry or you can have chemically bound water. Actually, now that I say that, I'm not entirely sure that this is what the RILEM says, but I'm sure that this was what the ASTM draft valve says. So chemically bound water is another method that you can use. It's a thermogravimetric analysis with maybe an easier or less sophisticated setup than a TGA itself, but it is a method that also measures total reactivity. And both will get you, both calorimetry and chemically bound water will get you a reactivity measurement, a total reactivity measurement. Now, besides the fact that I'm a little biased because I'm a calorimeter guy, I would indeed note that the main advantage of calorimetry here is that you still get the continuous measurement that you would not get with chemically bound water. And this continuous measurement tells you something about reaction kinetics. You have this continuous curve, and it is very telling. And we'll see in a few examples later that it's actually quite interesting. The other thing that the RILEM tells you, and the SCM2, is that you want to mix externally in a high shear mixer. And then they say we should cure at 40 degrees, which means setting the isothermal calorimeter to 40 degrees temperature, then record data for 168 hours, which is 7 days. So it's 7 days is sort of a compromise between enough time to see a good indication of reactivity, but not too long to make it tedious. And if you have to wait for a whole month, it's sort of meaningless. So let's look at this a little bit more in detail. The mix externally part is something we want to focus on. And because we're calorimetry people, we wanted to check what the influence actually is on mixing externally versus mixing internally in the calorimeter. So we made a few experiments, and we said, let's try different things. So we took a calcined clay, which is highly reactive, and we tested it in a calorimeter at 40 degrees C, but using 3 different mixing methods. As you can see, the black curve is using a high shear mixer, as you probably all have one in your lab, typically the Hobart mixers. And the red curve is using what we call the spoon mixing method. We use a little plastic spoon. With some of our calorimeter models have those large sample cups, 125 milliliters, and they're very easy to use in that way. And we have noticed over many, many years of utilization that, in all honesty, this is the most reliable method. When you do the plastic spoon method, you get very repeatable results. It's very reliable, very easy to control. It's actually a very good method, even though it looks so unsophisticated. So that's the red curve. And on the green curve, we had a true internal mixer, a good working true internal mixer. And you see that those curves are quite different. You look at the same material, same conditions, it's just the mixing that is different. So let's step back a little bit and say, so why don't we actually want to mix internally? Why does RILEM say, and ASTM will also say, that we should mix externally? Well, in general, you would like internal mixing. There's nothing wrong with it, because internal mixing enables you to get the reaction, the true reaction, really from the time zero. You have it in the apparatus, you mix in there. You're absolutely certain that you will miss nothing if you mix internally. However, the problem is it's been impractical for many, many years because of what you see on the picture. If you look at this picture, what's wrong with it? Well, what is wrong is that you see a big lump of material in there. It's poorly dispersed. It didn't work very well. It didn't mix very well. And the reason for that is that traditionally, the mixer that were used were just a stirring mechanism. It's just some stirring mechanism. This looks like a hockey stick, and the thing goes round and round and round. And it's quite effective to mix liquids, but for pasty substances, viscous substances, so take a material that has a high water demand and the mix gets a little stiff, and you get that. And the worst part of that is not even that. The worst part is that you generally don't notice until the test is finished, because the whole device is inside the calorimeter. And after 7 days, when you take your sample out and you look at it, and then here comes the exclamation point where you say, oh, I have to redo the whole thing, because if you see this kind of lump, you know that your results are wrong, that whatever you get is not exploitable. So you have to repeat the whole test. You just lost 7 days. So it's something that is impractical in the real world in practice until now. So in turn, what we try to get to is something that mixes better. So let's go back to these curves and let's see if it's worth pursuing internal mixing and try to make it better. Well, when you look at the difference here, you really see that if you have external mixing, you will miss out. No matter what you do, you will miss out on some early reactivity. So that may not be a problem with materials that are not highly reactive in the beginning. Take a class F ash, not much is going on for quite some time. But with materials that are quite reactive, a class C ash has some early reactivity. You would have anything that is there's a high surface area, like a silica fume, a metakaolin, calcine clays in general, or clays in general would have a high reactivity. You do miss out on something. Because if you look at the black curve, because of the temperature difference we have between the mixing temperature, so the ambient temperature where the mixer is located, and the actual curing temperature in the calorimeter, well, we have to throw out practically the first 4 hours, because that curve, the black curve, dips in negative territory for the first 4 hours. And it's not because there's an endothermal reaction in there, it's because the temperature of the environment where you mixed the ingredients was below the 40 degrees. Right? And this difference, this issue is exacerbated. The more temperature difference you have between your environment where you mix the materials and the calorimeter, the deeper this curve will go and the longer it will take to recover. And so you miss out on this whole range of data in the beginning when you mix outside. And that difference is not negligible. In many cases, it represents about 100 joules per gram, which is substantial. It's something that you do not want to miss, especially with highly reactive materials like the clays and these things. So if we could mix internally, we definitely should do it. Now, what we want is this. If you look towards the left, you see we have the left-hand sample where you have that lump, and this is exactly what we don't want. What we want it to look is like the right-hand sample where you have a nicely mixed homogeneous paste, well dispersed, right? And at Calmetrix, we all, of course, I present all this and I make all that fuss about it because I say, well, gosh, I mean, it's possible, and we developed it, so it's not awfully complicated. We developed the mixer, and I will show a short video. It's only 20 seconds. It shows how it actually unfolds while it's mixing. And let me start the thing. So here we have, so here you see how you put this mixing device into the calorimeter, and of course it stays there for a couple hours so that the material stabilizes, and then at some point you can launch it. But what's interesting and important to see is what happens inside when you actually mix. So you will see here that there's a comparison. On the left-hand side, you have the conventional mixing, which is just stirring the material by going round and round and round. On the right-hand side, you have the enhanced mixing with some vibrating action. And you can just see the difference. There's not much I need to say to this. You see how it clumps on the left-hand side and how quickly it forms a paste on the right-hand side. And while they look alike, they don't operate the same way. They're definitely, the left-hand side is just a normal stirring as we had until now, which prompted people to not use it. And the right-hand side is the solution. So summary of that is evident. In this case, what you get poor dispersion, incomplete hydration, incomplete reaction, and what you measure does not represent the truth. On the right-hand side, you have a good dispersion, so you will have good reliability, repeatability. The sample is well mixed. This is what you need. So it's definitely doable. There's no question that it can be done. And now that we have a system to mix internally and mix efficiently, now that it exists, let's just use it and see if we can capture the early reaction. And let's just test the whole thing. And let's look, as we do that, at the other recommended guidelines that we have in RILEM and ASTM, in the upcoming ASTM. So we say curing at 40 degrees C and record data for 168 hours. Okay, so we did that. Now it gets more interesting because now we actually, yes?
Yes, let me, I'm sorry to jump
now
in.
We're actually going to look.
There was a question I want to go ahead right now, if you can.
Oh, sure.
Yeah. So Steve Farrington asked, I think on the slide, maybe right there or maybe above, in the example of external mixing with the first part of the curve below 0, I guess that's probably that one curve that had the 3 curves on it with the different mixing techniques. in the example of the external mixing with the first part of the curve below 0, was the reference vial or inside the calorimeter and already at 40C?
Yeah, it was inside the calorimeter already at 40C. However, it would not help having the reference also externally, because you would just introduce two variables in there, because you would have a temperature gradient that is on the reference side and a temperature gradient that's on the sample side, and they're not necessarily the same, because one is being mixed, the other one isn't. And so you still have the unknown of what you actually get. It's the unknown part in the beginning of the overlap of different things that makes it non-exploitable. So in the beginning stage of this curve, you have a part of the curve that's heat of dissolution, you have of the salts in there, you have a part of the curve that is due to the temperature gradients, and the part of the curve that's actually the reaction that we want to look at, the true reactivity of the material. So because you don't know how much is each, it gets very complicated to do something with it. And because of that unknown, you can do nothing with it. So the best solution is still to try to eliminate some of those factors. So it's easy to eliminate the temperature gradient by mixing internally, right? So for traditional Portland cement, it's less important, because in the beginning you have the illuminate peak that is not very useful in calorimetry to begin with. And then there's some studies where you use it, but in 95% of cases, you will not really look at the illuminate peak. And then you have a dormant phase, and after the dormant phase, things start to get interesting. And so you have ample time. You can mix externally, and you have ample time to wait for it to stabilize. That's in a normal Portland cement. But if you want to look at reactivity of materials, of SCMs, and some of them are really reactive in the beginning, you want to capture it from the beginning. There's no need to play around with references outside, inside, because you can actually just mix inside, and you make your life easier. And we do have the mixers available.
Yeah, just questions here. I think related to that same point or same question, but Neil Burke was asking, why not preheat materials?
These materials were preheated. Even when you preheat the materials, the fact that you have it outside, when you preheat materials and you work at the calorimetry temperature that's close to ambient temperature. So let's say, for example, you have an ambient temperature of 20 degrees C and your calorimeter is set at 23. There will be very little difference, because when you have the materials outside and you have them there for a couple of minutes to do your mix, it's okay. Especially the water has a high heat capacity, so it's quite okay. But when you have the calorimeter at 40 and your ambient temperature is 20, or the calorimeter at 60 and your ambient temperature is at 20, very quickly even if you preheat the materials, they go from 40 to 37, and this is it. And then you get this negative peak, because calorimeters are sensitive; they measure that difference very well, and it takes some time to recover. So preheating works well when you mix externally, when the temperature gradient between the calorimeter and your ambient temperature where you mix is not very large, right? The larger it is, the more iffy it gets. So we did some tests here. So now using our internal mixer, since we see that it works quite beautifully, so we tested different materials, and yet it gets interesting because you can really see a curve with how they compare in relative terms one to one another. And we did this at 40 degrees C. And you see in blue, you have the calcined clay. Then in orange, you have metakaolin. In yellow, silica fumes. They go down from the highest reactivity to the lower. Then you have high calcium fly ash, so class C ash in green. And then you get in this brownish color, you get an F ash, a low calcium ash. And then you get ground glass in pink. And finally, in black, you would have a perlite as the least reactive in this. Now, what we see here is that clearly for the highly reactive materials, the three that you have on top, they're easy to see, easy to distinguish. Things work out well, so you have a clear distinction where you can see the reactivity very quickly and very clearly on those materials. And then for the lesser reactive materials on the bottom, you really have to wait for a long time before you can see something and be assertive about it. If you look after 60 hours, for example, distinguish between the ground glass and the perlite, difficult, even after 72 hours. And then there's always a lingering doubt when you have low signals like that, is that how much of that is actually noise the slightest error, a little bit in calibration, or the slightest noise level that you have because the reference was not right, or something that wasn't totally perfect, you could actually get results that are a little wrong in there. So you would want more signal to noise ratio for sure. And so here you see that the method has its limit, that the method that I said was initially developed really to test clays, and for clays it works well. But when you get to those less reactive pozzolanic materials, you have to scratch your head and ask yourself, is that good enough? And so, of course, the first thing you think about when you have a reactivity that is a little low and you cannot see much is, what do you do about it? So one obvious thing to do with most chemical reactions is to say, well, let's just raise the temperature a little bit and see what happens, right? So RILEM says 40 degrees C, but why wouldn't I try something a little higher? Why would I go to 60 degrees C? So 60 degrees C actually makes sense. Why not? If you want to do it and get a faster reaction, you could very well try. Now, there's a couple of things that that make it iffy in some circumstances. For one, the problem when you have 60 degrees C is that the temperature gradient between your ambient temperature where you mix and your curing in the calorimeter at 60 degrees, that this temperature gradient is higher. And as we said earlier, it creates more disturbance. So you lose even more of the initial curve. So that sort of defies the purpose, unless again, you have an internal mixer. If you have an internal mixer, then you're good, because no external mixing, no temperature disturbance, and you can go up to 60. So that's the good news for us, because we actually do have an internal mixer that works. So we can do those tests at 60 degrees. So another reason is that all the calorimeter models, they have sometimes a little trouble operating at 60 degrees, and that's any of the calorimeters that were from the first generation will have a little bit of that trouble. So it makes it difficult. But truth be said is that today's models that are sold, they all operate very well at 60 degrees. And if you can operate at 60 degrees in the calorimeter and have a stable temperature environment, and at the same time you have a reliable mixer, and let's go for it, let's try. So we did. So when we look at the difference between 40 and 60 degrees on those higher reactive materials, we still have the blue is the calcined clay, the orange is metakaolin, the yellow is silica fume, and on the bottom we actually have quartz as an inert material. So you see it's essentially flat. If I zoomed in, you would see it's noisy, but it's flat compared to the others. And you have the dotted lines are at 40 degrees C, and the solid lines are at 60 degrees C. So as you see, there's two things that you can derive from that. For one, it doesn't change fundamentally anything on how you would interpret the data. You get the same results. So they're still ranked the same. They still they max out. They get asymptotic at the same value. The metakaolin is about 650 joules per gram, and whether you test at 60 or at 40, it sort of ends there. But in fairness, there's still a difference, because the way it climbs faster, it really tells you that for those calcined clay, metakaolin, and silica fume, almost after 36 to 40 hours, you're done. You can stop the test and do something else. You don't have to wait longer. So you don't have to wait for 72 hours, let alone 168 hours. This acceleration is actually useful still, even on high reactive materials, because it gives you the same result much faster, right? And of course, when you have the right mixer, the mixer that works well, you capture this early reaction, so it's all beneficial. If you did that with external mixing and you have to throw out the first 4 hours, you wouldn't get the first climb, the initial climb. It would take longer. But with the internal mixer at 60 degrees, there's still a benefit. But I can understand if people say, why? Why do I do 60 degrees? 40 degrees gives me the same result. Now on the lower reactivity materials, it's the same concept. We still have the same colors. So for the high C fly ash, the ground glass, the perlite, etc. We have the dotted lines are 40 degrees C, the solid lines are 60 degrees C. Here you see there's quite a big difference. For one, what's interesting is that you do not have to worry anymore when you're at 60 degrees. You do not have to worry about signal to noise ratio. Now you're definitely at levels where the signal to noise ratio is very much okay. So what you look at now, you can look at results in confidence. The other thing you can see is that right now, instead of having to wait for 168 hours, you can basically, after 3 days, you can start ranking those in terms of reactivity. After 72 hours, you already get results that are usable, that give you a good indication of how reactive those materials are. Now, what I said earlier in the presentation is that it's interesting to see the continuous curves because it tells you something about kinetics, right? So what you see here, for example, look at the class C ash in green and at the ground glass in pink. So you see that the C ash is more reactive in the beginning. It climbs faster, but essentially after 3 days, they caught up to the same value. So it just tells you that they get to the same stage of reactivity at 60 degrees, but taking different paths in the reaction, the different speeds at different times. So it tells you a little bit of how those materials work and how they react. Now, on top of that, the 60-degree thing about activating those materials is not completely stupid as a temperature, because this is the kind of temperature you would easily reach when you have mass concrete and it's an insulated environment. You would actually go up there. So it represents quite well what happens and how these materials react, how reactive they are in the real environment, in the real world. But when we do our experiments and we try to find new materials, we should probably not restrict ourselves to something as restrictive as the temperature here, because we see in 40 degrees, for example, as you can see here, it doesn't tell you much on low reactivity materials. When you push that to 60, it starts getting more interesting. So it's good to experiment around, and actually it's good to do it at several temperatures. And why not do it at several temperatures and actually calculate an apparent activation energy and do some modeling and derive something? I mean, it opens the door to other things. So I think if you already have the calorimeter, you might as well experiment a little bit, because that's what science is about too. So we just not just following protocols, it's also experimenting to try to find better ways to be more efficient. So for us, using the calorimeter to its good purposes, if you have the right internal mixer, you can go up in temperature, you can go down in temperature. It depends on what you want to test. I mean, the RILEM and ASTM guidelines are excellent guidelines. They put the industry behind a single purpose. It's absolutely perfect. But from there on, I would dare to experiment a little bit. And that actually brings me to my conclusion here, is that conclusion for us is evidently we're big fans of isothermal calorimeters, so no question about that. We think it's a powerful tool. It's a powerful tool in general. We think that particularly in the context of assessing reactivity of SCMs, it has a lot of advantages. For one, calorimeters are really easy to use, and compared to many other things, clearly the sample prep takes only a few minutes. Data interpretation is very visual. When you look at the things, there's a lot you can tell just by looking at it. You can analyze in more depth. But when you look at curves and compare them as a comparative tool, it's a really convenient tool. And you have the part of continuous measurement. There's hardly anything that gives you such a good continuous measurement, so reliable and that you can look at, where you can look at how things evolved along the way in the reaction kinetics. Calorimeters tend to have excellent repeatability because the relative simple sample prep has not too much room for error, and mostly also because the temperature in the calorimeter, in this curing chamber, is extremely stable. And then it's actually quite cost effective, because as much as, and like with any capital expense, when you look at it, the initial cost looks high. If you compare this to the cost of the infrastructure and the operating cost you need for cubes, I mean, if you want to do your cubes right, you need a curing chamber that's much larger than the calorimeter. That costs money. And if you do your cubes day in, day out, every day, and you do all those cubes to test or cylinders for strength testing, all the hours that go into it and breaking them and coming back on Saturdays to get to break them at the right time, all this is very cumbersome and very costly. So we shouldn't forget about that. So I think it's a cost-effective tool, all in all. Second point that we want to make is that, well, thank you, RILEM and ASTM, for providing the framework and the testing methodology, because it actually puts something on paper that we can hold on to as a good starting point when we do our research. Just don't forget to experiment a little bit more and make it better. And with a good calorimeter, you can actually easily use internal mixing and get compelling results even for lower reactivity SCMs. So to me, there's no real reason to restrict ourselves. We should just use the tool to the full extent of what it's meant to. And with that, well, it means that I actually concluded this here today. So we can open up for more questions as long as you want, as long as you have time. And thanking you again for your attention, everybody, for being faithful and listening to the end.
So Neil is asking, if I put 20% fly ash with cement and compare joules per gram of cement, it is higher with fly ash. Doesn't that indicate that the fly ash is generating heat? ? Much easier experiment.
Yes, it indicates heat, but it would be hard to quantify and to be sure that it's only from the fly ash. So you of course, I mean, one thing that I should mention is that if you use the synthetic Portland environment, you measure reactivity, but that does not preclude and should not preclude to also repeat that kind of test with a given cement. So if you have several materials that you test with the synthetic Portland environment, you should also test them with a given cement, because there's other things that come into consideration. There's actually the distribution of particles, there's a packing effect, there's interactions with some other components in the cement. And you should even test it with the cement and admixtures, because an SCM can react a certain way just with pure calcium hydroxide and some alkali. It will react slightly differently with certain cements because the chemistry varies a little bit, and depending also on the particle size distributions and many other factors. And it will vary even more if you have admixtures in there. The chemistry gets all changed when you have admixtures in there. So definitely you should do all that testing. They're complementary. It's not one or the other. They should all be done. But they're all easy with the calorimeter.
Great, thanks, Mark. So Abdul from Clemson asks, in case we have a curing temp set up at 40 C, what is the delta between ambient room temperature and calorimeter temperature you would recommend for less noise in the data? So I guess he's talking about just the differential between the environmental temperature and the.
If you want to do external mixing, so ideally you want the ideal situation is you want no temperature gradient at all. So you want to limit it to the minimum. It's not really a recommendation. It's just the closer you can get to your actual temperature that you have in the calorimeter, the less effect you will have. And what I mean by less effect, it means the signal will stabilize quicker. Typically, when we do external mixing in our little cup with using just a spoon, which is there's less disturbance than doing it in the high shear mixer, we generally after about say 45 minutes, you can be pretty sure that you have no more effect of the temperature gradient when your calorimeter is let's say at 20 degrees and your ambient temperature is somewhere between 18 and 23. So these are benchmarks, but there's no straight answer to that. You should just be as close as possible to the actual temperature.
Okay, and question here. Oh, I guess I'll just a follow up there. I meant even if we have internal mixing. I guess what he's talking about. And just is there any?
Okay, so even if you have internal mixing, you typically would put the materials in the mixer, and the mixer is inside the calorimeter, and it would stand there, and everything would be there to stabilize to the temperature. So you would leave it there for about. That depends on the system you have. If you have our system and you have the large cell system, is 125 milliliters, you would keep it there for solid 3 hours. Be sure that the temperature of the material stabilizes to the calorimeter temperature as they're inside the mixer, which is inside the calorimeter. If you use the iCal Flex, then 2 hours to be safe is enough, even less than that, because it's smaller sample sizes and it gets stabilized quicker. But you can actually check that by looking at the signal on the calorimeter. When it gets really flat, you know that the temperature of the materials have reached the isothermal temperature, and you can start the internal mixing.
Yeah, I think, Mark, actually probably what Abdul is referring to is if you're doing a test inside of the calorimeter at 40 degrees C and your ambient in the lab is 23 degrees C, is there any reason to increase or decrease the differential between the ambient temperature and the calorimeter to maximize?
No. Now the calorimeter is built to maintain the temperature at 40 degrees C. So the ambient can be 23 or something else. It's okay. The calorimeter will maintain the temperature very stable inside. Of course, like with every calorimeter and every type of apparatus like that, if your ambient temperature fluctuates, you'll see small fluctuations in your calorimeter too. So you have to keep it stable as possible in your lab. But no, you don't have to do anything. The calorimeter is a curing chamber that handles its temperature on its own.
Yeah, the only issue, Abdul, I think maybe we've talked about this before, maybe, but you know, obviously, if you're at the extremes of the temperature range of any of the calorimeters, you know, if your lab is really, really hot and you're trying to go down to really, really cold temperatures, then it, you know, that becomes more of an issue in terms of temperature control more than anything else. But so hopefully we answered that question. The internal mixing, Era's question is for everyone else. Internal mixing allows capture of the initial critical illuminate hydration reactions. Just how early can meaningful heat versus time data be collected in your system?
So when you have the internal mixer, you capture it from time zero since the time the water hits the first grain of cement. However, of course, here again there's an overlap. So we got rid of the temperature gradient, and that's great. But there's still an overlap because you have the heat of dissolution of the salts in there. So that's something that I don't know how you would strip that out. So when you see that first peak, it's the illuminate reaction combined with the heat of dissolution of those salts. So it's still not perfect if you want to see the illuminates only. You would also have the mixing energy, but generally the mixing energy is lower than these other two. So it would not really make a difference, and it's more consistent from one mix to another. So you still have that overlap, but you can capture the actual heat release from time zero completely. There's no lag, no nothing, and generally what you would do, you would capture it because it's a peak that is a little sharper in the beginning. Instead of measuring every minute or so, you would measure every 5 to 10 seconds. So you capture most of it.
Mark, there's
I hope that answers.
Here, but if you can maybe put the slide up with our contact information as we're finishing up here, and make sure that if somebody has a question, they can get in touch with either myself or Mark. So Anna asked the question: does the system need a calibration procedure? And I guess you could talk generally.
Yes.
For the both calorimeters.
Yes, all calorimeters need a calibration procedure. And so you generally have a choice when you calibrate an isothermal calorimeter. You have to use sort of a reference, something that you know exactly what heat will be released, and you use that as the benchmark, and then you calibrate the result you get against that. So you make it match with the reference. That's how you do the calibration. So to get that reference heat, you can either use a known cement powder. For example, ASTM, the CCRL lab sells those calibration cements. That's one way to do it. But when you do it at several temperatures, sometimes it's good to do electrical calibration, because electrical calibration, you place a resistor in the calorimeter, or it's already there sometimes, and it generates a known heat that you know because you measure the electrical current or the voltage around the resistor, and so you use that as a reference. So electrical calibration is another way. Our calorimeters can handle both, right? So irrespective of which model you have, you can do one or the other, and so you can choose what is best. But these are the most known methods. There's other methods. You could use acid-base titration in there if you wanted to. Anything that you know, where you know exactly what heat value it releases, and you can use that as a reference.
All right, great. So yeah, Mark and I will. I think we've got we're up to date on all the questions that were asked. We'll stay online. So many people still online. So certainly, if you have questions, we'll stay here until the bitter end. But other than that, hey, listen, I appreciate everyone attending today, and thanks again.